So now that we've spoken about the evolution of the sun, let's talk a little bit about the structure of the sun. What do we know about what's inside the sun and how big it is and the different zones of the sun? So like most stars and even the Earth, it has a core in the center, and around the core it has an area which we call the radiation zone, where most of the radiation or the heat, the energy, goes out in the form of radiation. This goes out to a distance of about 300,000 kilometers, and then we have the convection zone. The convection zone is where we have the physical motion of material, like you can think the boiling of water in a pot, and this goes for another 200,000 kilometers until we get to what we see as the surface of the sun. This we call the photosphere. This is where the light is coming out from the sun and arriving at the Earth. And as mentioned before, the temperature close to 6,000 degrees Kelvin, whereas inside the sun we're talking about millions of degrees Kelvin, and so it's much cooler at the surface than it is inside the sun. And then, similar to the Earth, it has an atmosphere around the Earth. The sun also has an atmosphere, which we call basically the chromosphere, and this goes out for another 100,000, another 5,000 kilometers, and is also much hotter actually than the surface of the sun. So this we all get from looking at the sun from the Earth and from models of the sun. And if we want to actually look at the additional parameters, one interesting thing about the sun is that it's not stationary. It also rotates like the Earth around its axis. But the sun is not a solid body like the Earth. It's basically a ball of gas. So it's interesting that the equator actually rotates much faster than the poles on the sun. At the equator, it rotates about 25 Earth days to do one revolution. At the poles, it's about 37 Earth days. And this is rotating in similar direction to the Earth. If we look on the North Pole of the sun, it's going anti-clockwise, the rotation of the sun. Now, if we zoom into the surface of the sun, we can see that at the surface of the sun, at what we can see these convective cells, which you can see zoomed in here. This is from a satellite image showing that we have these convective cells where the lighter colors are where we're having hot material coming up to the surface. Hot is lighter or brighter, and then the sinking motion of the material is where we see the darker lines. And so these little boxes or these little pixels you can see in the high resolution image are actually these convective cells of material coming up to the surface, which is very hot, and then sinking down again into the sun. Now, something interesting we've seen, and we know about this for hundreds of years, is that sometimes when we look at the sun, we see spots, what we call sunspots, on the surface of the sun. And you can see a few of them here. These are dark patches on the sun. And as we'll talk about also a little bit later, and as I just mentioned, darker areas are cooler than the brighter areas. So these dark areas are actually slightly cooler in temperature. And we've known about this, as I mentioned, for many years. In fact, here you can see, first of all, at the bottom left, images or pictures which were drawn by Galileo in 1612. You can see here these 4 different images for the 24th of June, 25th, 26th, 27th, where these black areas on the disk of the sun represent the sunspots that he saw in those days. And actually, Galileo, because he could actually make, as what we would call maybe today, an animated GIF, you can see on the right-hand side that if you track the sun and you watch it, you'll see that these sunspots are actually rotating and going around the disk of the sun with time. And so it was actually Galileo, the first person to actually estimate what the speed of rotation is for the sun by tracking these sunspots as they move around the surface of the sun. So from watching these sunspots, we know exactly how fast the sun is rotating. And then on the top left, you can also see an image from a satellite zooming in onto the sunspot. You can see the dark area of the sunspot. And when we go into the background, again, you can see these convective cells, which are having the bright yellow is where the hot material is coming up, and the gray areas are where the cooler area is going down. Now, these sunspots are huge. We can see here in this image on the top right the comparison with the size of the Earth. So you could basically fit the Earth a few times into these sunspots. They can be thousands to 50,000 kilometers in diameter. And as we also saw with the rotation, the image of the solar disk, they can last for days, weeks, up to even months. Sometimes the same sunspot can actually go around, one rotation will come back, and we'll see it again, say 25, 27 days later. So these are very large features on the sun, especially if we compare them to the size of the Earth. Another interesting phenomenon is that they often come in pairs. You can see here in this image on the top left that we have two sunspots together. Also on the right, we have two sunspots together. We'll talk about that in a second of why they come in pairs. Now, how do we get these sunspots? What do we think produces these sunspots? So the Earth, the sun's magnetic field, we can think of it being similar to the Earth's magnetic field, where we have a north pole in the north and we have a south pole in the south. But because we don't have a solid object, you can see in this animation that basically because the equator is rotating faster than the poles, the magnetic field lines get twisted. You can think of them like spaghetti, being twisted and deformed, and some of these magnetic field lines close to the equator will pop out of the surface of the sun, and this is what is producing actually the sunspots. These are actually the locations where we have storms, solar storms on the sun. Similar to we have storms here, we have storms on the sun which produce huge eruptions of material and can cause even damage to satellites and power systems on the Earth. And there's a whole new field that we're not going to talk about in this course called space weather. Similar to this Earth's weather, we also have weather in space, which is produced by these storms which occur at the location of these sunspots on the sun. So if we zoom in a little bit more to these sunspots, we can see that below the surface in the light blue, we have these convection zones. And again, if we have the sinking matter, you can see here on either side of the sunspots, and this is where we're having cooler material, and hence the sunspots are actually darker at the surface of the sun. When we look at what's happening above the surface of the sun, we have this loop which is going up into the atmosphere of the sun, which we call a prominence. These prominences are actually the magnetic field lines coming out, but how do we see these magnetic fields? Well, most of the material in the sun, because it's so hot, are either protons or electrons or ions, which are charged electrically. And when they interact with the magnetic field, they actually get trapped in the magnetic field. And so these particles can go up and come down and can actually trace out the magnetic field line, producing what we call these prominences. And sometimes these magnetic field loops actually snap, and then the material can actually flow out into space, and we call these solar flares. So all of these are different terms related to the storms which occur on the sun, and these storms are occurring in the location of the sunspots. And here we can see actually a real image of the sun's surface, this animation, again with the relative size of the Earth down here at the bottom. These are huge features on the sun. In this image, we're not looking in the visible, we're looking in the ultraviolet, and therefore the sunspots actually look very bright because they're giving off a lot of ultraviolet radiation, the yellows. But if you looked in the visible, you would see dark spots on the sun's surface. And these loops in the atmosphere, again, are related to the magnetic field lines, which are kind of popping out of the surface of the sun, and then these charged particles which are going up into the atmosphere. And the only reason we can see these loops is because these charged particles are scattering the sunlight, which is going out back to the Earth, to our cameras, so that we can actually see these features because of the scattering of the sunlight off these particles. And here's another quite beautiful animation. These are real images of the surface of the sun. You can see these ribbons of the magnetic field of the sun, which are taking these charged particles up and back down into the sun's surface, very dynamic. And again, where they connect to the surface of the sun, these are the locations of the sunspots we see on the surface of the sun, where in the visible they would be dark in color.